So in today's video, I'm going to be looking at 10.3 and 8.5. 10.3 is very similar to what we just covered in 10.2, where we looked at confidence intervals for the population mean. I'm going to be doing the same thing here, but looking at confidence intervals for the population proportion. 8.5 takes us way back to what we did before all this central limit theorem stuff and looking at confidence intervals. It takes us way back to what I should have done before spring break and just didn't get a chance to do that. So I will cover that in this video. But first, let's start with 10.3. What we're trying to do here is we are trying to find a confidence interval where I am a certain percent confident that my population proportion that I'm looking at will lie within this range. It will lie within this interval with a certain level of confidence. Okay. First of all, taking us back, I very quickly want to mention this. If you want a point estimator for your population proportion, okay, so we're trying to find a way that we can estimate our population proportion. Two ways we can do it, either by using a single value or by finding an interval that it will lie in. The first thing we will do is for a point estimator for the population proportion. Okay, remember we call that P. Okay, a good point estimator, a good value that we can use to estimate our population proportion is the sample proportion, where I have taken a representative sample and I look at what proportion of people or things in that sample have that certain characteristic that I am looking for. And whatever proportion of people in my sample have that characteristic, I can use that as an estimate for how many people in my population will have that same characteristic. So a point estimator for the population proportion, P, is the sample proportion. P hat. Okay. We're going to use that again in a minute. We've also looked at this before. But now looking at my interval estimator. So I'm going to an interval that I want this interval to contain my population proportion. So an interval estimator for the population proportion. Okay. You may remember from when we covered this in chapter 9 that there is a Z transformation for the sample proportions, because our sample proportions, as long as there were certain properties that were fulfilled, our sample proportions could model a normal distribution. So they could take on this normal distribution as long as they satisfied, there were two properties, if you look back at 9.4, that they had to satisfy. When we do this, our Z transformation for our sample proportions was our sample proportion minus the population proportion over the standard deviation of the sample proportions. Remember that the population proportion was also the mean of my sample proportions. Okay, it was a good estimator for it. So we do our sample proportion minus the population proportion divided by the standard deviation of the sample proportions. Okay, plugging in our formula for our standard deviation of sample proportions was this formula here. So it was the square root of P times 1 minus P over N. Okay. Again, look back at 9.4. That's where we covered this. Just as a quick recap that I did mention in 9.4, sometimes you are not told what the population proportion is when you do this Z transformation. Okay. So occasionally, and we'll look at this in a second when we rearrange this stuff, occasionally you will have to, instead of using the population proportion in your standard deviation here, you may have to estimate that P using the sample proportion P hat, okay? You normally have sample data, you may not have the population data, okay? And we are trying to find a good estimate for this thing. So what I tend to do for my Z transformation is actually state it this way instead. P hat 1 minus P hat over N, okay? Where I have estimated my population proportion by my sample proportion instead, okay? Now, using this Z transformation, I want to find an interval estimator for my population proportion. So I'm going to use this formula to estimate this value, okay? Now, going back to what we just did in 10.2, you may remember that I said, we always said with our empirical rule that within 2 standard deviations of the mean, you should have 95% of your data. That means in our standard normal distribution, that between 2 and -2, okay, remember that 0 is the mean, standard deviation is 1. So therefore, in our standard normal distribution, 2 standard deviations either side of the mean takes us between 2 and -2. And between those values, we have approximately 95% of the data. Okay? And I said to you in 10.2 that in actual fact, it is 1.96 either side of the mean gives us exactly 95% of the data. Okay? Because we said that if we went 2 standard deviations either side of the mean, so if Z was between 2 and -2, the probability of landing in that range was approximately 0.95. Okay, there was a 95% chance approximately that we would land in that range. In actual fact, to get this thing to be exact, it's actually the probability that you land between -1.96 and 1.96 would give us exactly 0.95. Okay, so we can take that approximation out of it. Because that is true, what I'm going to do is plug some stuff in here. So I know that for my sample proportions, I can let Z, let me back up on that. So I can let Z, other way. There we go. I can let Z equal this thing. Hopefully I've got enough space to do this. Over N. Okay, and that is less than or equal to 1.96, which is equal to 0.95. Okay. I can rearrange this thing. So I can multiply up by this standard deviation term. So if I multiply both -1.96 and 1.96 by this standard deviation term, okay, I can then subtract my sample proportion all the way through. So I can subtract it from what term I would get here and subtract it from the term I would get here. And then I would have to multiply all the way through by -1, which will switch around my inequality. Whenever you multiply by a negative or divide by a negative, it always switches the inequalities, okay? And that will leave me with my population proportion in the middle and bounds on either side. When you do that, what you should actually get, when you go ahead and figure this out, you should get P hat minus 1.96 times this standard deviation of the sample proportions here. I'm going to shorthand that whole thing right now just so I have enough space. But all I am looking at here, when I talk about the standard deviation of the sample proportions, it was this term here. Okay, so I'm going to shorthand that right now to just be sigma of P hat, is less than or equal to P, which is less than or equal to P hat plus 1.96 times that standard deviation term is equal to 0.95. Okay, so I know that I now have bounds on my population proportion. It can be as small as this value or as large as this value, with a 95% certainty that it would land in that range. So I am 95% certain that my population proportion will land between this value and this value. Okay. Again, I'm going to now extend that to be however confident I want to be. In this case, we were 95% confident because we were looking at a 0.95 probability. So I was 95% confident here that my population proportion landed in that range. What I now want to do is extend that to be any percentage of confident that my population proportion will land in some specific range. So again, I'm going to write this all out, and it may look kind of weird right now. It's got very much the same setup as what our population mean had in the last section. But what we now have is if the sample size is sufficiently large, so remember for the population mean and sample means that we had last time, we had to have the n was at least 30. In this case, we have our two other properties that we have to satisfy for the sample size to be large enough. So if the sample size is sufficiently large, okay, if you go back in your notes for this, you'll know that that means that our sample size times our population proportion should be at least 10, and our sample size times 1 minus p has to be at least 10. That means that I have a large enough sample size, okay? And remember, this is kind of weird notation, but I want to keep with what we have all the way along. This confidence level that you have, so in this case you could be ones that we've looked at so far is like 80% confident, 90% confident, 95% confident, etc. You can write it like this, just be aware of that. But again, I'm going to draw this all out for you guys so that you can see it rather than using this weird notation. But the confidence interval for the population proportion P is given by P hat plus or minus some z value times the standard deviation of sample proportions. That can also be written as that z value and our standard deviation of sample proportions. Because we do not know our population proportion right now, we're trying to find an interval that it lies in. We only know our sample proportion. So I said when we do this, we are going to use that sample proportion within my definition of the standard deviation of sample proportions, just as an estimate, okay? So I can rewrite this as this, okay? And if you wanted to write it in interval notation, it would look like this. Okay, again, remember when you are looking for that z value, okay, we had the z value for the last one where we were 95% confident. We already know that that z value is 1.96. I just used that as an example. But if you do need to find that z value, we denote it as z alpha over 2 just as a notational thing. But if you ever need to find that z value, it's exactly the same as what we did in 10.2. So let's say you want to be 80% confident that your population proportion will lie within this interval. Okay, so quick example, if you're 80% confident, so you want an 80% confidence interval, okay, and you want to find that z value, go ahead and draw it out. Every time you do this, draw it out, okay? You know that you want to be 80% confident. So take that area to be 0.8. That would mean that 80% of your data is going to lie between z of alpha over 2 and negative z of alpha over 2 with 0 in the middle. 0 is the mean. We are looking at a z value here. We are in standard normal right now. Okay. We want to be 80% confident. So we've got 80% of our data is going to lie between z of alpha over 2 and negative z of alpha over 2. You want to find this value. Okay. This value here is only the negative of this value. Okay, and we want to find it. We know because this thing is symmetric and because I've got 0.8 in the middle, I should have, with an area of 1 under the curve, I should have 0.1 either side. So if I now want to find that z value, I always tend to find the negative of it just to make it easier. I know that to find that, I have to use inverse norm in my calculator. My area under the curve to the left of that value, remember to always plug in the area to the left, is 0.1. My mean is 0, standard deviation of 1, because I'm looking for a z-score. I am looking for a z value. This thing here would give me negative z of alpha over 2. Okay, so to find z of alpha over 2, just make that thing positive. Okay, so whatever value you get, it should be negative. Just make it positive. It's just way easier to deal with. Okay, so it's exactly the same. When you need to find that z-score here, it's exactly the same as what we did last time in 10.2. Okay. As always, you do not have to do this by hand. Okay, there is a function on your calculator that will calculate this interval for you. So if you go to stat, go across to tests. Okay, this is exactly where we found all the z intervals and t intervals from 10.2. Okay, if you go down, there should be on my calculator, it's option A. Okay, so you've gone to stat, you've gone to tests, and you scroll down. Option A on mine is 1 proportion z interval. Okay, so you want option A, 1 proportion z interval. Click that. And it will ask you for some information, and we are going to do an example so that you can see this. It asks for X, N, and the confidence level, okay? X is just the number of things in your sample that have that certain characteristic. It doesn't actually ask you for the proportion. It's actually going to find the proportion for you. So X is just the number of things in your sample that have the characteristic that you are looking for. N is the number of things in the whole sample. So X is the number of things in the sample with the characteristic. N is the number of things in the sample. So you should find with the notation that you have in your calculator. So if X is number of things in the sample with the characteristic, whatever characteristic that may be in the problem. N is just the sample size. Okay. That means that your sample proportion, the proportion of things in your sample that have the certain characteristic, is just X over N. Okay, so all you have to do is type in what X is and what N is, and it's going to calculate that sample proportion for you. You don't even need to do that. So this is the first example that I want to look at. And it says that we are looking at an environmentalist that wants to find out the fraction of oil tankers that have spills each month. And so they have spills. Let's keep that in mind as we go through this. Suppose a sample of 399 tankers is drawn. Of those ships, 296 did not have spills. So if 296 did not have spills, that means that the other 103 out of the 399 tankers must have had spills. Okay, so 296 did not have spills. The other 103 out of the 399 did have spills. And that's what we're going to be looking for. So keep that 103 number in mind as we go through this. Using the data, construct the 95% confidence interval for the population proportion of oil tankers that have spills each month. So we want the confidence interval, that should contain the population proportion, the proportion of these tankers that have spills overall in the population of oil tankers, not just in this sample of 399. We are looking at the whole population of oil tankers here. So whenever you get this particular type of problem where they have given you one sample, okay, you have one sample of 399 oil tankers, okay, and you want to find that interval that contains the proportion for the whole population that have that certain characteristic. So whenever you get a problem like this, you need to go into your calculator and let me change the screen here. Go into your calculator and you are going to go to Stat. Go across to Tests, and this is where we found Z interval and T interval before. But if you scroll down, all the way down to here, where it says 1 proportion Z interval, okay, you have one proportion here, okay, because you just have one sample. So you have one sample proportion. Later on, we're going to deal with particular problems where you're going to have two different samples. That would be a 2 proportion Z interval. But right now, we just have a problem where we have one sample, therefore we have one sample proportion. We are looking at one particular population proportion. So we're going to go for option A here. Click on that and it's going to ask you for some stuff like the Z interval and the T interval did, okay? It's going to ask you for X. That's the number of things that have the characteristic that you are looking for. So in this case, we want the number of oil tankers that do have spills, because we're looking for the population proportion of oil tankers that have spills. So we know in our sample that 103 out of our sample size of 399, so N is 399, okay, will have spills in our particular sample. The confidence level that we want here is 95%. So you're going to put that in as 0.95. And you go ahead and calculate. And this is the information that it will give you. This is going to be your interval, okay? So this interval will contain the population proportion, and we are 95% certain of that. Okay, then we have these two numbers here. We have P hat, that is just your sample proportion. So what they have calculated there is just X divided by N. So that's 103 divided by 399 will give you 0.258. And N we already know is 399. It will give you that information again. But this is our 95% confidence interval. So we know that our population proportion, the proportion of oil tankers in total that have oil spills, should be between roughly 21.5% and 30.1%, so 0.215 and 0.301. So the next thing that I want to look at is when they ask you for the sample size. Okay, so they have given you maybe the error and they've told you something about an estimated population proportion, or they have given you a sample proportion and they ask you what the sample size would be. Okay, now if you remember back again to what we did in 10.2 when they asked you for that sample size, I'm going to come back to my formula here. Okay, this is what we're going to be using. And we said that the error, when they give you what the maximum error allowed is, the error term is just this part here. Okay, it's the maximum amount that my population proportion and my sample proportion can differ by. Okay, so it's the maximum error between what my population proportion could be and what my sample proportion is here. So my population proportion can be at most this amount away from what my sample proportion was. Okay, so this term here is my error term E. So whenever they give you an error term, that's what they are referring. So as you can see, we have this formula for the error term. Now, if you think back to 10.2, there were specific problems where they asked you to find the sample size, where you use that sample size program in your calculator. And what that did was, given in that case you were dealing with means and standard deviations and stuff, you would input that data into your calculator and it would tell you the minimum sample size that was required. You can do the same thing here with proportions. So if they give you what they want their maximum error to be, so the maximum amount that they want to be away from that sample proportion p hat, they give you that maximum error E, and if they give you that sample proportion, so they tell you something about this many out of this many in the sample had this particular characteristic, let's say 3 out of the 5 people in your sample were right-handed or something like that, then you can go ahead and actually calculate what the sample size is. Okay, so they'll say, okay, we want to know the sample size with a certain level of confidence, with this maximum error, and with this particular amount of people out of our sample size having a particular characteristic, or this proportion of people in our sample having this particular characteristic. Okay, so with the sample proportion, the confidence level, and that maximum error, you can rearrange this equation to find n. Again, it's a terrible formula to find that sample size n by rearranging all of this. Okay, so what you're going to do is to use that sample size program that I put into your calculators, and you can go ahead and just put in the information from the problem into your calculator to go ahead and find that minimum sample size that is required. So this is an example of a sample size problem that you can get with proportions. So it says the State Education Commission wants to estimate the fraction of 10th grade students that have reading skills at or below 8th grade level. In an earlier study, the population proportion was estimated to be 0.22. So we have an estimate for the population proportion. That can also mean, because we use that sample proportion as an estimate for the population proportion in that error formula or in that interval formula, that is what we are going to use. So if they either give you what the population proportion was from an earlier study, or if they give you just a sample proportion that they have used, that is totally fine. So either an estimate for the population proportion or the sample proportion, that is what you are looking for. So that's 0.22. Then it says how large of a sample would be required in order to estimate the fraction of 10th graders reading at or below the 8th grade level at the 80% confidence level with an error at most 0.02. So we want our error term in total to be at most 0.02. So that entire term needs to be at most 0.02, and we want to be 80% confident. So in order to do this, as I said, you're not going to use that formula. It's too long and complicated. So we're actually going to turn to our calculators. And you are going to use that program again that I put onto your calculators, either sample size or SS2. I would recommend you use SS2. Okay. And you're going to run that. Now, last time when we were trying to estimate a sample size, we used that first option because we were looking at sample means and we were looking at that confidence interval. This time we are looking at a one sample proportion confidence interval. Then it's going to ask you what proportion you have. Now in this case we are using that population proportion that was given, or you can use that sample proportion if they give that to you as an estimate. That is totally fine. So you either want the population proportion from a previous study or you want the sample proportion. Either way, you want something that estimates that population proportion for you. So if we go back to our problem, we see that that population proportion was 0.22. We have an error of 0.02 and an 80% confidence level. So let's come back to our calculators. We have a proportion of 0.22. Then it asks for the margin of error. That was 0.02. And then our confidence level was 80%. So we want to put in our confidence level as 0.8. That means that the minimum sample size that we require in this case is 705 in order to have an error of at most 0.02.